design will help you to design the op-amps and all the analog blocks in FinFET design also. So basically, we need some characteristics of the devices. We need one black box. We consider, we as a circuit designer, we consider the devices as a black box, and we expect that devices to perform in a specific way. So that also we will discuss in this session. We discuss some control system fundamentals like stability, phase merging, and Bode plot, Nyquist plot. That will help you to understand the op-amp as well. So actually, please be attentive. It will be very, very helpful to you if you want to pursue the career in analog domain, and most of the interview questions also you will get from this also. So please be attentive, right? Let me share my screen. Actually, I haven't made a PPT. Actually, I thought that we might have to interact in between. So I will present through my OneNote, and just let me. So is it visible to you people? Hello? Response.
Yes,
Hello?
sir.
Yeah. So operational amplifier. So the one more thing that I want to tell you is why the op-amp means. So if you have seen that, you heard about that the op-amp require the high gain, and in a negative feedback system, if the high gain feed forward path we require, such as that because finally the negative feedback system during the feedback we want that the whole system will depends only on the feedback path, and the feedback path is only the passive elements. We don't want the feedback transfer function during the negative feedback to be depend on the feed forward transfer function. That we will see step by step. So the op-amp means the operational amplifier, and the basic operation that we want to perform is subtraction, addition, multiplication, logarithmic, integration, differentiation. So basically we all this operation we can perform through the help of the op-amp, right, in negative feedback. Why in a negative feedback? We will see that. So amplifier. So why we need an amplifier? Because the real world is analog, right? Let's say my speech. So my speech voice signal is a random signal, and it has to be amplified. Why it has to be amplified? Because I have to suppress the noise of the same level. My speech has a very low amplitude, suppose. Then the noise is also of the same amplitude coming from the surrounding. Then my signal power should be the higher than the noise power. Then I can process my signal, right, and I can suppress my noise. That's why I require the amplifier after the sensor. And then if that amplifier signal is passes to the ADC, and then the process is done in the digital domain and send it to the wire and reach to the sound system. This is just an example, right? So we need amplifier. That is a necessity of the amplifier. The second thing is, if we are telling that we are amplifying something, so what is we are amplifying actually? Is that we are amplifying a voltage? Is that we are amplifying a current, or we are amplifying a power? Basically, we are increasing the signal power. We are not amplifying a voltage or current, but basically our target is to increase the signal power. So let's say this is my simple basic building block of the amplifier. Input is V in, output is I want is V output equal to K into V in. Some K is some gain factor. Definitely I need some gain. And definitely the circuit has a VDD and ground connection, right? So as I told, I don't want a current amplification or voltage. I need a power amplification. So is that the power amplification? How can we get the power amplification? The question is. So let's consider the simple passive device, the transformer. The input is Vi. Based on the turn ratio, I will get the output voltage. So even we are getting the output voltage, that is N times the Vi. But we see the power that is always the less than the Pn, because this dissipate the power. This is a passive device, and the passive device always dissipate the power, and passive device can't use for the amplification. So we have to think of the another device, let's say the active devices, and that also be the non-linear one. Why not a linear one? Let's think. So this is a simple two-port network that I have drawn here, And first of all, let's say my source is Vs and the source resistance is RL. I want to transfer my power to the load resistance RL, right? So according to the maximum power transfer theorem, we have already studied I think in the second semester of the network analysis, that for this the RL should be equal to the RS, and for that the P output, my P output will be the Vs square by 4RL, right? And that is a less than P in. So that's prove that the passive element does not give the power amplification, right? So this is the thing. So what can we think? How can we give the power at the output at the particular signal component? So can we add a DC battery and give the power, external power? That is a good idea, right? So let's try this also. So here what I have done in a simple two-port network. Why I have taken the two-port? Because in real means in our case port network, that's why I am taking the two-port. So that output port, and I'm supplying, I am taking the help of the battery to get the extra power. But see, this thing is a linear and passive network. So linear, what it means, the linear means it has to obey the superposition theorem. What is the superposition theorem? The homogeneity and additivity has to be satisfied there, right? So in the output, we will see the power. It has a AC component, it has a DC component, but the one thing is there, if I have an input signal that is a V0 cos omega 0 t, then at the same frequency component, I will not get that power. Why? That is because the linear and passive element. But I want that omega 0 frequency component that is need to be amplified, its power has to be increased. That will not happen with the help of the linear and passive circuits. So I have to go for the non-linear active element. We can't get the amplification with the help of the linear and passive, as I already told, because the passive element always dissipate the power, so P output is also always less than P in. We need additional devices. We can't go for the linear devices, right? Because our main purpose is to convert the DC power from the external battery to the frequency component of omega 0 at the output. That is my purpose. So let's see the different devices what we have. Linear, non-linear, passive, active devices. I have made up one table here. So we can see that the non-linear active devices is BMOS, BJT, JFET, MOSFET, and how it's work actually. Means I am saying that it non-linear and active devices. It will work for the amplification. How? Like, right? There will be a doubt, right? How we can use it. So first of all, let's take the nonlinear characteristics, simple nonlinear device, any nonlinear device, I versus V characteristics. So in this nonlinear devices, if at this one particular point, let's say at the V point, I have input voltage V, I am getting the output current I, that's my operating point. So that operating point is decided by the DC battery. That means we are taking the help to decide the operating point, and we are taking the help of the DC battery. And surrounding this operating point, we can see if we apply the small signal perturbation, small signal, the term small means it depends on the accuracy we want. Though here we apply the small signal perturbation, so we will at the characteristics around the operating point, we will get the linear. That characteristic, non-linear characteristic is converted into the linear one, because we don't in mathematics the non-linear circuit has to be converted into the non-linear equation, and then has to be, that method is very difficult, right? So for the simplicity, even though there is a non-linear device, we have to convert into the linear approximation, and then with the linear tools like the differential equation, Laplace transform, and all that thing, we have to derive the expression and we have to solve it, and we have to come to the conclusion. Right, that is a method that we are generally following. Hello, yeah. So this is a thing, basically the nonlinear devices surrounding the operating point is behaving like a linear devices, and around that it gives the amplification to us. That means that whatever the statement that I have made, that I want that the DC power to be converted into the power at the frequency at omega naught. So this can I can work. This is working. By this way, we are using a non-linear device to work as a amplifying device. We will see further. Right? So let's analyze further. Means how we are using it. So for that, let's build some background in mathematical terms. So I have a simple non-linear two-port network, and the I1 is a function of V1 and V2, even the I2 is a function of V1 and V2. If we expand this thing, suppose I'm applying a perturbation delta V1 and delta V2, so definitely I will get the perturbation delta I1 and delta I2. If we write that equation in that terms and expand this Taylor series expansion, so finally we will get the expression in like this. In that expression, I will get the first order derivative with respect to the V1, first order derivative with respect to the V2, first order, second order derivative, and the second order derivative with respect to the V1 and V2. So here you can see that the delta V1 and delta V2 is a small perturbation. We already tell that, right? We already decided that the signal is very small. So this delta V1 square and delta V2 square definitely be a small value. So we can neglect it. So after neglecting, we will have this equation. Delta I1 is equal to derivative of F1 with V1, delta V1. So from this we can build a small matrix, 2 cross 2 matrix. This is a small 2 cross 2 matrix that we have already built. And this matrix now you can see that is a linear form. So now we apply the linear concept to come to the solution. Right, because we have assumed that the signal is very small. During the small signal, that nonlinear Kara is behaving like a linear, and we derive this linear equation. So if we plot the different curvature between I1 and V1 as a V2 as a parameter, I1 and V2 as a V1 as a parameter, and I2 as a I2 versus V1 as a V2 as a parameter, and I2 versus V2 as a V1 as a parameter, so the slope of this characteristics will give me this Y parameter. And this is basically the output is I, input is V, is Y parameter. We can derive this expression in terms of the Z parameter also, but now currently I have derived this expression in terms of Y parameter, right? So this is a thing. So and this looks familiar to you. This is a Kara of ID versus VGS. It's MOS Kara, and I2 versus V2 is ID versus VDS is MOS Kara. But we will come to the conclusion later. First of all, let's observe this. So here, that linear two-port network converted into the Y matrix, I have plug it here, and now I have a linear equation, so I can find the V2 by Vs, right? So my V2 by Vs after the derivation, I am not going to the deep derivation here because we don't have a time afterwards. I think we don't have a time, so that's why I am skipping some steps just to go to the intuition, just to build the intuition into your minds. Right, so V2 by Vs is equal to Y21 into Gs divided by this Y12, Y21 minus this whole term. So basically what this is a gain, right? And this gain I want to, I want more and more gain. We are greedy people. We want more and more gain, right? So to get the more and more gain, I need the denominator to be a very less. So see, in the denominator term, there is a term Y12. Y12, it means that the voltage at the terminal 2 and I am getting a current at the terminal 1. So is that the thing we require in a reality? It means in the output I am giving a voltage and I want some current in the input. Is that the thing I want? The reverse direction? No, that means the Y12 is 0 definitely. So after it, I have a term, this two terms, Y11 plus Gs and Y22 plus GL. That this term I want to reduce this term. So again, I have taken the Y11 is equal to 0 and Y22 is equal to 0. This will be clear to you, don't worry. So finally, I have this expression V2 by Vs is equal to minus Y21 times RL. So what is Y21 here? The Y21 is here, means 2, 1. That means 1 at the input port I am applying a voltage and the output port I am getting a current. That means that I output divided by V input. This is nothing but the transconductance parameter. So this is transconductance times the output resistance. This is nothing but the voltage gain. And this is the maximum voltage gain that I can get from this two-port linear network. But there is a condition is that this 3 is a condition. So it means that we need one nonlinear device that has this kind of characteristics. So let's find, right? So this is a Y parameter matrix that I want from the device. Y110, Y220, Y21 is there, and Y22 is 0. So this is a simple I1 versus V1 curve. Slope I want a 0. I1 versus V2. Y12 I want slope, horizontal slope 0. So this but I2 versus V1 I want a larger slope. That means the Y2 I need larger. That's why I have drawn the vertical lines. It's larger slope, right? Steep. And I2 versus V2, the Y22 is 0, right? A horizontal slope I don't want it, right? So let's draw that thing in terms of the y parameter equivalent model, and finally at the conclusion, last conclusion, we come to that our nonlinear device in a small signal approximation should work like this, and then I have built an amplifier. So this is my amplifier. This is a simple amplifier that I want and that I have derived from the nonlinear to the linear conversion around the operating point. So till now, what I told is the DC power I want to convert at the specific frequency. This can only happen with the nonlinear devices, but the nonlinear devices, the analysis is tough. So I have to approximate it to the linear one, and the linear one I have derived the y parameter matrix, and I am looking for the devices. Which device is giving me this y parameter network, right? So let's look the devices. I have already told that we will go for the MOS. So here is a MOS. Simple input VGS, IG is already 0, ID, VDS. So this has in saturation, we have the simple equation 1 by 2. Means I am ignoring the channel length modulation, so I haven't included the 1 plus lambda VDS term here for the simplicity, just for the simplicity. So ID equal to 1 by 2 mu n cos x w by L VGS minus VT whole square, and if we derive the GM, that is a del ID by del VGS, that means del I2 divided by del V1. So it gives the transconductance parameter mu n cos x w by L VGS minus VT. So that's my Y21. That means that if I plot this SCARA, ID versus VGS and ID versus VDS, so surrounding the operating point, even though this characteristic is non-linear, surrounding the operating point, this SCARA is a linear, and this giving me a gain. This giving me a current of time GM times the VGS, and that current I am passing through the resistor and I am converting into the voltage. So I am getting a gain of minus Y21 into RL, that is GM into RL. So through the MOS we can build the amplifier. That's my conclusion here, right? And even we can see that the Y22 is 0 only in the saturation region. Only in the saturation region we are getting a larger GM. We want a more gain from this. So even the diode region is also giving a gain, but is less. The maximum gain you can get is in the saturation. In the saturation region, our requirement is satisfied here, right? You can see that the ID versus VDS SCARA, the slope in the saturation region is 0. The horizontal slope, that means the Y22 is 0. Del ID by del VDS is 0. That's what I want. So that is satisfying my need. The MOS in the saturation region can work as an amplifier. That's I have proved till now. So let's go. What is our main target was? The input is a V in. I need a fixed K times V in the output. K is some gain factor. But thing is that in the real life, we can't simply build this kind of the things. Simple MOS amplifier. Actually, what happens across a process, across a temperature, and across a supply variation, there is a PVT. This is called the PVT variation. Due to this PVT variation, there might be a chances that your gain will vary, and your input is also varying. Your gain is also varying. That we don't want, right? We want our gain to be fixed for the whole input range. So in this kind of the scenario, let's say the example of the AC. So surrounding temperature is changing, my atmosphere temperature is changing. I have fixed my AC temperature to 25. So even though the room temperature is varying from 15 degree to the 50 degree, I want my AC to be work at the 25 degree itself. That means that at the irrespective of any condition, I want the gain. K is K. So for that we have to use a feedback. We have to use a feedback, right? So, and that's the negative feedback. So what we are doing simply, let's take the example of the bike. Means I want the speed of the 50 kilometer, and right now the speed is 60. So difference is 60 minus 50, 10. So 10 kilometer per hour, I have to increase my accelerator, right? And if I want to increase my speed to the 90, then I have to increase my accelerator more. So there is a rate of acceleration. Similarly, same kind of the AC example, if my temperature difference is used, my AC conditioner has to work at the higher rate to reach my reference temperature. If the error is less between my temperature, the temperature I want, and the room temperature, at that time, the AC conditioner has to work at the lower rate. So, in physical significance, we can see that means we are sensing the output, we are feeding back to the input, we are generating the error, and that error we are using it to drive my V output. right? So if we intuitively see this G block has this kind of the functionality that the input is a step, the error is a constant value, right? Let's say in the speed 10, 16 I want, or 50 I have, that's 10. If 80 I have, 80 I want, and the 50 I have, that's 30. That's the constant value, right? And I need an acceleration rate at the output. Means I want to drive fast, I want to drive slow. That's the rate, that's the ramp signal. That means that the intuitively in the negative feedback system, this G block is an integrator, right? At the input of the integrator, if you apply the step, you will get the output ramp. That means that in the negative feedback system, this G is an integrator. And this integrator we also want in our amplifier also. So this is an integrator, and this I plug it here in my negative feedback system. But one thing, here you can see that the slope is different for the two different curve, and that is different for the two different curve, and that is based on the value of the error. That means that my integration rate is different. Slope is different. That means integration rate is different. That integration rate, how can I decide? That is a property of the integrator, and that property of the integrator I am denoting as a omega u. Just think this is a simple constant right now. As the talk goes, you will get clear idea. So at the end, you think you have to connect the many dots and you will get the clear picture. I will try my best to get the clear picture of the op-amp, right? Fundamentally. So please be attentive. So this is omega u is the integration rate, right? Then let's just simply take this V output. Here the V is integrating error, right? So omega u integration VE dt. Just I want to show you here that the plots of two different omega u. Let's say here the omega u is a frequency that I will prove later. For the lower value of the omega u, you can see that the integration rate is low. Means integration rate, that means ramp rate is low, slope is low. For the high rate, for the higher value of the omega u is higher. For the different value of the V, you can see that. So the slope is depend on the omega u and the V itself. So this is the thing. If we approximate, if we derive the unit step response of this closed loop transfer function, I haven't brought a derivation here. Just simply plug this here, just to get the intuitive feel. Don't worry, just to get the intuitive feel. So here the V output has a two terms. First thing is, due to the initial condition, there will be a decaying exponential. Like you have solved the differential equation, complementary function, and particular integral. You will relate these things there also. Even you can relate here also, right? And the another thing is the desired output that will also be the reaching the output with in an exponential manner, right? But you can observe the thing that e raised to minus omega u by k into t. That is the main thing that I have you to focus, and you can say that is t by tau. Tau I am denoting the time constant, and that is equal to k by omega u. So here, and one more thing I want you to observe is that if you plot the V output versus t, the initial slope is equal to 1 by omega u. That means that if your omega u, the integration rate is higher, the initial slope is higher. It will reach the output to the very fast value, and it will settle quickly. If you take the settling time is generally 99% of the final value, around 4.6 tau is approximately the 5 tau. So the time constant is k by omega u. See, the time constant is again depending on k and omega u. If the gain k is more, than if it means that if I want V output is equal to 10 times V in, and V output is equal to 100 times V in, for getting a more gain k, I need more tau. That means that my settling time is more. First thing. The second thing is, I want you to observe is there, if I have a more gain k, let's say the 100, and to reach settle quickly, I need larger omega u. That means the omega u is larger, the tau is less, so that means definitely the settling time will be less. That means here is a conclusion. In figure you can see the gray one is actually is reaching the output with the higher gain, and blue one is reaching the output with the lower gain, and the initial slope is same for both because it's the property of the integrator. We are using the same integrator for that. But the thing is that for the different value of the gain k, I am getting a different settling time. That is a key thing that I want to focus you. Now let's take our integrator and analyze in terms of the frequency domain, Laplace domain. If you see in the frequency domain is nothing but omega u by s. So if you plot the body diagram, the approximate body diagram, so it has you can see there is a pole at the origin, so already minus 20 dB per decade slope will be there, and at the omega u point it will touches the 0 dB axis, right? So it is that is the 0 dB axis. So I already told you in the previously that is integrating factor, and that integrating factor is nothing but the UGB. So it is UGB. UGB means unity gain bandwidth. That means the gain curve is touches the 0 dB line. That is my frequency is UGB, right? So it is UGB. That means you can relate that what that integrating factor is nothing but a UGB of the op-amp. That is a op-amp actually. That integrator is a op-amp. The ideal integrator. This is the characteristics of the ideal integrator, and that's why I have gone through this mathematical things. Just want to build the background. The real thing will come in last 20 minutes. But if you have this background, then real thing will definitely will get clear in your mind. So that's why I will take the 1.5 hour to just build the background. So this is the integrated omega u is just the integration rate, right? So let's plug in these things into our closed loop control system, omega u by s, and derive the transfer function, right? So v output by v in equal to the k divided by 1 plus s k omega u. You can say that means the transfer function tau, time constant tau is k by omega u, and the omega b you will get one pole here, that's 1 by tau, and that is omega u by k. So if you plot the closed loop transfer function here, you will get this kind of the thing, the 20 log k at the DC, and after the omega u by k, that's the pole frequency, and you will get the UGB, that's omega u. The main thing that I want you to note down is that if I am plotting the loop gain is simply omega u by s, omega u by ks. If I am k is actually the 1 by k, I am taking a fraction of the output to the input. If the 1 by unity feedback, then 1 by k is a 1. So I have drawn this curve. If you see in the loop gain curve, the orange line is for the unity feedback and the blue line is for the specific feedback. Then the feedback factor is always a less than 1 because that made up of the passive element and then doesn't have a gain. So it's definitely has a less than 1. So that loop gain, you will see the UGB change to the omega u by k. The point you have to note here is that till the frequency omega less than omega u by k, you can see the feedback is very strong, and due to that the closed loop transfer function you will get is a 20 log k. The 20 log k is what? If you analyze, if you see that feed forward transfer function is g and feedback transfer function is h, then during the feedback, negative feedback, we want g divided by 1 plus gh. The gh is very high, so it get cancelled, and approximately is 1 by h. So 1 by h is nothing but k here. So the thing is that I want you to note down is the frequency less than omega u by k, my feedback is very strong, and due to that my whole control system is act like its transfer function. It depends only on the feedback network. But the frequency more than the omega u by k, you will see that the transfer function following the feed forward transfer function, that is a g. So that is the main thing here. This is a boundary line that the loop gain UGB is setting here. Even you think you can take a note that the loop gain UGB is a pole of a closed loop transfer function, and that's the reason. That is the main reason we draw the Bode plot for the stability for the loop gain. We analyze the loop gain in Nyquist plot, even other stability criteria, and that is the main reason. Right? That is a control system concept. I think some of you have gone through it. So same thing, weak feedback and strong feedback. So for the unity feedback, let's say the unity feedback, if we take the unity feedback, my range of the frequency over which my feedback is strong is more. If I have mentioned here the green area, 0 to omega u by k. If k is 1, then that green area, that means the frequency range is more. That means that I can get a strong feedback for the larger range of the frequency. That the point that I want to make here. So unity feedback, why we are taking unity feedback? Basically, the unity feedback will give you a worst case stability. Why the worst case stability? We will look into it. But right now, just take this point right now. Okay, so let's take, this is already the closed loop transfer function. We are applying some input. This is a signal system concept. I think you have gone through it in sixth semester. I think I had in sixth semester subject. So Vp cos omega 0 t, the at the output, the magnitude at the omega 0 I will get, and the phase at the omega 0 that is added. So the point that I want to make you here is that the frequency less than omega u by k, that is the UGB of the loop gain, at the output I will get a gain k. So simply that Vp has to multiply by the gain k, and I will get a phase minus omega tau. So that phase is added. But for the frequency omega greater than omega u by k, for the larger frequency, my output has decreased with, output is decreasing with the omega. You can see in that the output equation is omega u by omega. So with the omega is increasing, output decreasing. Definitely this thing you can see from this graph also. Yeah, this here. Oh, just a minute. Here you can see, right? So this is the thing. Thus I want to make a point. There is a boundary line. That's loop gain UGB setting, and loop gain is what? G into H. Suppose I am taking worst case phenomena, the H is a 1, that means the loop gain is only a G, and that is my feed forward transfer function, and that is a op-amp. And this omega u that's making the boundary is the UGB of op-amp. That's the point I want to make you here. That's the UGB, and that's the UGB that we will calculate when we analyze the circuit in a MOS level. But from this block diagram, I just want to tell you that my omega u is making the boundary between the strong feedback and the less feedback, and based on this, my settling time, even my ringing stability is dependent. That's the point. You please make it here. So the higher the bandwidth, I need higher omega u. That means my op-amp u omega u must be a higher. The integration rate is higher. Means what I am telling to you. So this thing is op-amp. Actually, what we are taking a two different signal, we are generating an error, and we are just passing to the integrator. This is a op-amp, right? So just I have noted. The thing is that let's build this op-amp. That means let's build this integrator. So how can we get an integration? Think in terms of simple way. I have a capacitor. Across the current, means across the voltage, I have VC. The current flowing through this is IC. So the voltage across the capacitor is simple 1 by C integration I dt. So I need a current that is a function of the difference Vp and Vn. That is the input of my op-amp, and then I will pass that current through the capacitor, and I will get an integrator. This is a simple thing, right? See that I have built it here. I need one block that takes the difference, generate the current, passes to the capacitor, and it will integrate. And once it will integrate, that's how my purpose that I use in that I want in my amplifier. So that is the thing. So here, so I need voltage to current converter, right? Because input is a voltage, I need a current, and that is also single-ended current. I has a differential input, so I need voltage control current source here. So this is a simple voltage control current source with the transconductance GM, and that current I am passing to the C, and that is giving me an integration. And this thing is known as an operational transconductance. This is a simple OTA structure. This is not a op-amp. This is a simple OPA. It has some non-idealities. We will go step by step. So if we derive the expression here, and the final expression is Vc is equal to 1 by C integration of IDT, but I is nothing but a GM into VD, and VD is nothing but a Vp minus Vn. So we will get the thing here that Vc is equal to GM by C integration Vp minus Vn dt. The thing I want to note you here is I get this omega u, and I compare this thing with the previously that I mentioned the omega u. Here this omega u is nothing but the GM by C. And the GM is a transconductance of the OTA, and see the capacitor from where I want from which I want to flow that current. So that's my UGB. So this is the thing, that's omega u is GM by C. Oh, now I am putting the circuit, the small signal equivalent circuit, into my closed loop transfer function. But the problem that I am getting here is that I want that there is a two parallel parts C and R. And I want that GM into VD current, that current has to be flow through the C, because I need an integration for that only, not for the, I don't want the current that is to be flowed into the resistor path. So what can I do? The simple solution, I can put one buffer there. the voltage buffer there. So what is the voltage buffer? It has a Zn input impedance is very high. So definitely the current will not flow through that, because the current always choose the least significant impedance that the capacitor will have at the high frequency. So that will flow through that, and the output impedance is 0. So basically I have modified my op-amp from the OTA to this. So this is my op-amp now, and it has a UGB of Gm by C, right? So next thing, I am adding one by one non-idealities. So let's consider that in my feedback part I have a delay. So what will happen? So I am sensing the output. Then after some delay, I am comparing. So after some delay, I am comparing. So previously, if my feedback signal is 0, then Vi minus 0, my error is large. My indicator already pushed that Vi output to the very high value. And then after some time, let's say after the 5 seconds, I am getting that VO to the VF. And then my error is a very small value. So my indicator will push back to the downward value. So I will get a ringing in the output. This is the intuitive way that I want to tell you. That means the delay in the path, loop gain path, will add, will finally leads to the ringing in a step response. And that ringing is basically due to the phase margin, due to the pole location in S plane and phase margin that we will look. This is the intuitive way that is just I want to tell you. And how this delay will come? So you know that when you build a circuits, the every node has a capacitance. Every metal has a resistance. So you will get the RNC in parallel there also. Even in the indicator also, this kind of the thing you will get, and even in the feedback factor also, this kind of the thing you will get. So due to that, you will get the poles and 0, and that will add a delay. And if you analyze that poles and 0, so that the even in a control system, you can see that the first order system is always a stable system. But if you go for the second order system, although it is a stable system, that is but for the stability of, if I don't have a control over the some parameter zeta and omega n that we will see, then my pole location is different, and I will get an underdamped response, that is a ringing, and that ringing is undesirable, and that ringing is here. So I am relating that second order system with delay and that pole. I think you got clear. So here is delay in the system. Yeah, this thing was already clear. So let's think that I have added one pole in a feed forward transfer function just to get the second order intuition, and how this pole will be added, that also I will, this will connect you dot afterwards. So 1 by S plus 1 divided by 1 plus S by P2. Why I have named that pole P2? Because due to the omega U by S, we got already one pole there, right? So that pole, this pole is the second pole in a closed loop transfer function. So we derive the V output by V in, you will get this kind of the expression, and this expression I can relate with the second order expression, S square plus 2 zeta omega n plus omega n square. So zeta I will get 1 by 2 in this equation, and omega n at this equation. That don't worry about this, you can go through it. Just I want to tell you that please focus the intuitive here. And the analog design is all about the intuition. So that's why if you plot the step response here, then for the different value of the zeta, you will get the different step response. If you relate this thing here, just relate this thing, these two, the S plane pole location and the step response. If you relate this S plane pole location, definitely don't worry, this whole derivation you will get into the control system textbook. So if the zeta greater than 1, then the second order polynomial will have two real roots, zeta equal to 1, two roots are same, zeta less than 1, two complex root we will get. So if you relate this thing with the step response, then for the zeta less than 1 you will get a ringing, that's under damped. Zeta equal to 1 you will not get a ringing, zeta greater than 1 you will get a sluggish response. So if you go from zeta greater than 1 to the zeta equal to 1, then you can see that both the poles are coming nearer to nearer, and then split into the complex plane, and it will create the complex conjugate pole, and that complex conjugate pole will lead to the ringing. And as the pole is near to the j omega axis, then you will get a more ringing, and that more ringing, that means the phase margin is lesser. Actually it adds the more phase in the system, we will see into that, don't worry about it. It's add the more phase into the system, so that the phase margin is very less, and we are getting a ringing in the output. If my pole is on the j omega axis, then our output will get oscillate only, sustained oscillation we will get. So So that kind of the thing is there. We will relate it. That's why I have noted here that, and my pole P2 is near to the UGB, then zeta less than 1. For the zeta greater than 1, pole P2. This thing also will get clear in your mind afterwards. Don't worry. And from, if you go from zeta greater than 1 to zeta less than 1, my phase lag is increasing and the phase matching decreasing. This thing is also you will get afterwards. You have to connect the dots after it. So let's analyze this. This is loop gain omega u by s and another pole p2, right? So magnitude and phase, that phase is minus 90 minus tan inverse of omega v2. Here I have just plot Nyquist plot of it, and if you don't know the Nyquist plot, just take a thing here that just I am plotting here. There is a real GH axis and imaginary GH axis. What I am trying to plot is that for the different curve, red curve, green curve, and this curve, violet curve, this dotted curve is what the magnitude of GH is equal to 1. So take this thing, if my transfer function is g divided by 1 plus gh, so if my 1 plus gh term is 0, the transfer function will be infinity, right? This is a simple thing we all can understand. So when it will be a 0, that the gh equal to minus 1. So as equally when the gh is equal to minus 1, then the transfer function is infinity. That means I will get a sustained oscillation there that I don't want, and that is a actually a bar question criteria for oscillation. We don't want that. So here that means that if you say that the GH equal to minus 1, that magnitude has a unity and the phase is minus 180 degree. So if you see that the minus 10 point on the left hand side axis is minus 180 degree axis phase. So we don't, we actually this curve, 3 curve is actually that phase is different. You can see I have marked there. From minus 10 point, the violet curve is nearer, then green curve is separate, far, then red curve is too far. So actually, as you are approaching this minus 10 point, your phase margin from 180 degree is reducing. You will get a ringing. That's the point I want to make here. That's the point I want to make here. That my phase margin will get reduced because the phase lag in the system is more. From the red to the violet one, the system phase lag is more. The system phase lag is more. My margin from 180 degrees is less, and so that I am getting a ringing in the output. And that is what my stability criteria, and that is what the phase margin definition we will get from here. What is the margin? Phase margin from the 180 degree axis, we need a certain margin of the phase that it not touches that point. If what happens, it touches that point. What happens if it touches that point, minus 10 point, then my magnitude GH is equal becomes a minus 1 and my transfer function becomes the infinity. That's I don't want. That's why it is called a margin, phase margin, margin in a phase, right? So let's go. Here I have plotted here one simple Bode plot of loop gain. So initially already have one pole at the origin, so minus 20 dB per decade, and then it touches the j omega axis. So that is it touches the my 0 dB axis. So it's the omega u loop, that is a loop gain frequency, UGB of the loop gain, and then I'm getting a pole P2. So at the P2, due to the P2, I will get minus 40 dB per decade gain. And if you plot the phase curve, this is a more interesting point. If you plot the phase curve here, they already have a minus 90 degree phase shift initially, but due to the P2, I will get the change in a phase to minus 180 degree. There is a transition. So if you think that here, the more and more, let me draw here one thing to help you understand. If you pole P2 is more and more near here, you will get this kind of the Kara. Then my phase margin will be less. That means what I am trying to relate is that this is my UGB in the omega axis and this is my P2. So if your P2 is coming near and near to the UGB, this thing, this margin, this phase margin, I will get reduced. Because the curve will shift like this, always shift like this. And this will reduce at the omega u if you take the phase margin. Actually, what is the phase margin? Phase margin is equal to 180 degree plus 12 of GH omega gain GC. Omega G is nothing but the UGB. So at UGB, you need an angle. So here is UGB. I need an angle here. So if you shift this curve here, then my margin will be less. My margin will be lesser and lesser margin. So my phase margin is get decreased, and that I don't want. That's the reason I want to kick out. I am using a word kick out this P2 far away from UGB, and I want to make the system simple as a single pole system, so that the single pole system is always a stable one, and that's I want, and this you will get clear afterwards. So now this is my OTA, but the thing is there in the OTA I will have output resistance, that's the non-LID. So what this output resistance will do, let's see. So here the difference, due to the difference I am getting a current GM into VD, that current is actually passes to the R0 and C. So due to the R0 in a transfer function, GM into R0 divided by 1 plus SC R0, the previously I have a pole at the origin that is got shifted at the minus 1 by R0 into C. If you plot the loop gain Kara, the blue Kara is shifted into the violet one. I will have, due to this R0, I have a finite DC gain and one pole. Previously I have a pole at the origin, now I had the pole at the certain frequency, right? So that is a thing that I am getting here, finite DC gain I am getting due to this R0. And why that R0 will come, please keep in mind that we will think, you will see the circuit and you will get that, oh, this is R0. In practical circuit we will have some specific resistance. So this is the thing, but so what we'll do, what this R0 will do, okay, from this circuit we come to know about that it will give a DC gain, finite DC gain, and what this DC gain will do, what this bloody fellow will do. So if you see this circuit in at the DC, so the DC, the capacitor will get open, this current GM into VD flows through this resistance R0. So voltage will get here at this node is at this node my voltage will be GM VD times R0, and my V output will be GM VD times R0. So and that fraction of that output voltage is VO. Coming to the input, and then again if you solve this equation you will get this thing. So you will get finally this thing. So in this thing, the gain K, I want ideal gain, means I want V output is equal to K into V in. But this term is extra I am getting because of it. What this term is, let's see. So let's find the relative error. Relative error means ideal gain minus actual gain divided by ideal gain. So ideal gain is K, the actual gain is this. So if we calculate the relative error, you will get approximate value is 1 by GH, just I have simply noted here in terms of the G and H. And that is basically you will come to know that is K divided by GM into RO. So from this you can see that this is a gain, if the finite DC gain. If this gain is higher, my relative error is less. And that is I want. Do I want error in the system? No, I don't want error in the system. So that what I have to do? I have to make this GM into RO to be a very large value. Right? The first thing is I need a high gain op-amp, high gain amplifier, high gain op-amp. First thing, because I don't want a relative error. The second thing is, you already have seen that I think the G divided by, in negative, how the negative feedback fellow is working, G divided by 1 plus GH, transfer function. So I want the GH to be very large value, right? GH is very larger than 1. So I can approximate this thing as a 1 by H. And then we already seen that the frequency omega u less than omega u by K, this thing I am getting. That means the thing is that I need this thing. GH greater than 1. That means that H is already 1. I need gain greater than 1. So gain I needed for negative feedback purpose also, and for the relative error also purpose. This is a two purpose. I need a higher gain, right? So this is a point that we have to take a note here. Now, the another problem is that with this OTA, that I want the current to be flow through this capacitor, right? But this capacitor, the current is also flowing through this resistor. But I want the integrating action. The integrating action only happens when the whole current is flowing through the capacitor. So let's use another technique. I have the current here, this current control voltage source. In this circuit, what you can see is, that my current is I. It's current control voltage source. My output the current will not flow through here. So definitely it is flowing through the here. And when it flows to the capacitor, V output is equal to 1 by C integration IDT. So what I can do is, whatever the current I am generating here, sir, GM into VD, that current I am passing through this cap. So See here. But that current direction, I want in this direction. That current direction I want is this direction. Previously I have in this direction, but I want is this direction. This is a previously I have in this direction. Oh, what happened? Previously I have in this direction, right? But I want this current to be follow in this direction. Then and then I will get V output positive thing here. So this thing I am getting in this direction. So that's why I have reversed this polarity. You can see. Just I will reverse this polarity. Minus plus V1. So I'm getting current in this direction, and this direction current I'm passing to this capacitor. I am getting a V output. So my intention was to build a integrator, and that integrator I'm getting here.
Sir,
right or not?
Can I ask out?
Yeah, please.
Oh, thank you. Our point for this circuit was to reduce the current flowing through R0. So how does this do that?
Yeah. Actually, our point is that. Our point is that my current, I want to build a integrator, and how we have decided that we can get the integrator. We get the GM into VD current that passes to the capacitor only, but we have that non-linearity body fellow R output right there, but we don't want that the current flows to the R output. So what we have used another technique. This is a technique.
Okay.
This is a technique that
so
I
in this technique, no current flow. Okay, in this technique, no current will flow through R0 because of virtual ground.
Yeah.
Okay.
Got it? Yeah. So this is a technique that So this is a technique that we have built to flow the entire current to the capacitor, and that will finally give me Eureka. Oh yes, I got it. V output is equal to GM by SC into VD. That's why I want it, right? So this is my integrator, and this integrator has a omega u, that is the UGB. We already seen the loop gain, that is the GM by C. Please keep this number. Means I think you got I think it will get clear into your mind, right? So this is the thing. So again, this is the op-amp here. I am using a op-amp to build the op-amp here. Is this the proper way? No. So again, take this thing into the OTA, means operational transconductance. We can build the OTA. So we have built it here. Again, I have put GM2 here with the OTA, another OTA, and taking the feedback through this capacitor. I am using this GM into VD current and passing this to this capacitor and getting here this. So here you can see that the RO1, RO2, C1, C2. What is this fellow? The C1 is due to the parasitic there, and after we will see that the C1 will also in that parallel you will also get the Miller capacitance. That don't go fast, and here definitely we will have final output resistance RO1 and RO2 of the first stage and the second stage. The C2 is actually consists of the parasitic cap and the load cap also, right? So this is my op-amp, those. Finally I got my op-amp at the block level, but let's understand more and more. Oh, it's already a 2. Okay. Actually, I will take some more time, half an hour more time, because it's very interesting for me, and definitely I want you to make a clear picture of the op-amp from fundamental point of view, from the base to the building. Yeah. So let's see here. One thing you can see that. Hello. Is anyone is asking a question or no?
No.
One thing we see that with the negative. See, GM2 is negative here, is positive, is a negative gain. This path is one path and another path is this path. So there is a 2 parallel path, and across a capacitor or across any impedance there is a negative gain. So you will see the Miller effect there. So what the Miller effect is? See, one thing is note that we are generally saying a Miller theorem. Miller is not a theorem. Miller is an effect, and based on that we have derived the theorem. Miller is not a theorem. Miller is an effect that David Miller has derived. You will find that paper also. And see, there is a 2 node A and B. Across these 2 nodes we have 2 parallel paths E and minus A. minus A is inverting gain. Even if it is not inverting gain, we can see that also. So if we apply the delta V perturbation here, I will get here minus A times delta V perturbation at the another node. So across capacitor, what I will get the voltage is 1 plus A into delta V. So capacitor voltage is 1 plus A into delta V. Definitely the charge will be more, and the equivalent impedance for the capacitor will get changed. So let's look this point here, that here at node A, here at node B, I am actually giving a delta V perturbation, and here I am getting the minus A times the delta V. See, from traveling from A node to the B node, I am getting the positive C into the negative thing. So in between a one point, I am crossing a zero. This is a zero, and the 0 point actually depends on the gain. Got it? See, for this gain A, my 0 point is this. My this gain A, my 0 point is this. That means that zero virtual ground point, I'm shifting between A and B. That it physically means that between A and B, in this kind of the scenario, we get the impedance looking from to the A side and looking from to the B side is different with respect to the grounds. Right? That is the thing that I want to make you here. So here, that's the impedance is Z1 here, this impedance is Z2. Similarly for this, the impedance is Z1 here, impedance is Z2 here. Right? If I have a positive gain, then if I have the positive gain, then this is the thing. You will not get the 0 dB axis, you will not get. But if I have more positive gain, then this is not actually I have to consider immense. I have to take this here because it will take a time. You will get the negative resistance, and that's negative resistance you can use to build an oscillator. Even though you will have a positive gain, larger positive gain, forget it. Means just you want negative gain with capacitor. So thing is that the impedance looking from to the A point is Z divided by 1 plus A. So the capacitance looking from to the A point is C times 1 plus A. That means that in this circuit, at the A point, this fellow, let me change the color. This fellow, A point, this is CC, this will build one Mueller, will have a Mueller effect, and will add capacitance here at the node A. That's the point I want to make. And due to that, see this capacitor at the node A, the equivalent capacitor. What is the pole? The equivalent resistance into equivalent capacitance. This the equivalent resistance you can see is R1 only. Here, the equivalent resistance you can see is R1 only, but the equivalent capacitance you can see that the C1 in parallel with the Miller cap, and that Miller cap is CC times 1 plus gain A. And this gain is too large, sir. And the CC we have added is also in terms of the less value of the picofarad. So this is very large. This P1 will become a less. That means that this fellow will come near to the origin, and this will be dominant pole in the system. We will see. This will be the dominant pole in the system. That's why I noted here, dominant pole. At the port node B, if you find the pole here, so at the node B, you will get you will see this kind of the circuit there. This is the node B. We have to find the R equivalent and C equivalent. The R equivalent is already the RO2, and the another impedance there is we have to see. And the C equivalent is already the C2, and the another is there we have to see. Right? So if we see that there is a GM2 in the GM2 there is a CC in parallel, and this node is C1. But let's ignore this CC and C1. Just sort it. So this will GM2 will equivalent impedance will be a 1 by GM2. Because we are applying a current Vx, applying the voltage here Vx, and across the resistor, across this 1 by GM2 resistor, you will get a current same. So this equivalent impedance equal to the 1 by GM2. Same here, this concept I am using here actually, so that the equivalent impedance from looking from this is equal to 1 by GM2 CC divided by C plus C1. Why? Because this Vx actually, and if you'll see, this is a Vx. You can derive with your own. Actually, it will take a time if I go into this kind of the stuff then. This is the Vx actually. This is controlled by the Vx. You can see that, and by this way, if you apply it, you will get it. So Z out is equal to 1 by GM2. The equivalent impedance is GM2 by CC divided by this. So finally my pole P2 is what I will make 1 by R equivalent into C equivalent is equal to G equivalent by C equivalent. I can write. The total conductance is ZO2 plus GM2C divided by C plus C1 divided by total capacitance, and total capacitance is C2 plus actually the total capacitance will be at node B will be this. This is C2 and this fellow CC and C1. The C2 in parallel with the 2 series thumb. So that's the thing here. You can see in the circuit here. So actually why I am doing so fast, because I have a practice, and if you go through this you can also do the practice and you can get an intuitive way to get the pole and zero, and that's what the analog designer has to develop that skill.
Sir,
So
sir, how did we get Z out as 1 by GM2? There's only one port through which current can flow in that setup. When in that figure 2, where you have shorted the
now derive there. Now derive here. What you will see. See, now my Vtex is a Vx, right? So I am applying the voltage here Vx. Okay, I am current getting here this. So what is my impedance? V by I. V is Vx and I is GM2 into Vx. Vx Vx cancel. What I will get? 1 by GM2.
So which port is that? It's ground. So it's like if you look at that 3-port network, what I'm seeing is current is flowing through one of them, but where does it come out from in that 2-port network? In this network, in that figure, current is coming in from the Vx node, but where does it come back from?
Sir. To get the output impedance, have you gone through the circuits to find the output impedance?
Yes, sir.
Yeah. So what we are doing in finding the output impedance, this is my circuit, linear and passive circuit. To find the I want to find the output impedance, right? This is like, let's say ground node. And just I am applying a V test, I am applying a I test, and the R is equal to V test by R test. This is the same thing I am doing here.
Okay, sir.
Got it?
Yeah.
Got it, or you still have doubt?
Still, like, I'm not understanding which is the node that where both the grounds are connected.
Arey, sir, see, this is already ground, right? This is already ground.
So we assume that current is flowing out from the plus node?
Arey, no, yeah.
Because we usually don't make that assumption in the...
No, we are not assuming that thing. Consider the small signal equivalent model of this. You will get the small signal model of equivalent model this, right?
Yes, sir. Yes.
Right or not? Right?
Yes,
so
yes, sir.
Yeah.
So we assume there's one more port through which current is coming out from the...
No, man. Why are you getting confused? Because in this path, the current will not flow. The current has to flow in this way. Because in the op-amp input impedance, op-amp input, the IG is 0. The op-amp will be made of this kind of the structure, right? Gate structure, and the MOS, the IG is 0.
Yes, sir.
Right?
Yes.
Now you got or not?
Yes, sir.
Okay.
Yes.
Sorry, huh? You got now?
Yes.
Actually, मुझे बुरा लगेगा यार, तुम्हें पता नहीं चलेगा तो. Sorry. Well, let me take a 1 minute break. I want to take a water. Sip of water. So, sorry. The thing is that now we have multiple path here. So whenever in the system, whenever in a circuit, you have multiple path from A to B. You will have a, see, whenever you traveling from this to this, either this thing will be added in a positive way or either this thing will be added in a negative way. That means A plus B or A minus B. And in the transfer function numerator, you will get this kind of the thing. That means you are getting a 0 there. Simple. So here we are getting Here in this thing we have a two path. First part is this, second part is this, right? So that I have made it here. Where is that? Oi, where is that? Here. That I have made it here. So here you are getting plus and minus. Actually, the both are the not additive in the same direction. So that's why plus one term is plus, another term is minus. We will derive that thing here. I will not go into the derivation because it's already a 212, right? So just introduce, I want to tell you that there's two paths. I will get a zero, and that zero will be in this form a minus b. So that zero will be in the RS plane. And the RS plane 0 always add a phase lag into the system, and as the phase lag into the system, that will always degrade my phase margin. That we will see. And the zero value from this derivation of the circuit we will get is GM2ACC, right? And why I have named it CC is a compensation capacitor, so that's why we will come to know about it. And finally the UGB, that's what my targeting UGB. There's the transconductance of the first stage, and that current is passes to the coupling capacitor, and that's what I want. So it's GM1 by CC. So now we already see that this zero is troubling us. This bloody fellow is troubling us, right? So we want to eliminate this bloody fellow. So how we can do this? So in the derivation you can see that 1 by SC minus 1 by GM2. So if we add one more term 1 by GM2, so this plus and minus term will get cancelled mathematical way. Plus and minus will get cancelled, and you can eliminate mathematically. That means you already eliminated the zero in mathematical way. So how we do in the circuit? So in the circuit we can see that actually this GM into VE current is passes to the capacitor, and if this GM into VE current passes to the element who has a resistance of 1 by GM2, then this term and this term will get cancelled out. So that's why I will add one resistor here, and its value is 1 by GM2, so that my right hand plate 0, RS plane 0 will get cancelled, and I am safe from the phase margin degradation. And but due to this RJ added, I will get a pole. It will create this kind of the structure around that GM2 transconductance, and due to this I am getting a one pole, but that pole is, you can see the R2 is already the GM2, and this three capacitor in parallel, so it will be a list one, and the C1 will be a list one, the C1 will be a list one, and then P3 will have a higher frequency. With the higher frequency, that means that it is far away from the UGB. You will see here. See, this is a body plot diagram that I have drawn. This violet line is basically loop gain, and that is for the unity feedback. But with the feedback, what we will get with the feedback we will get the term 20 log h, and that is a less than 1. That's why we will get h is equal to 1 by k, and then less than 1. That's why I have plotted in yellow line negative. But so if we add g into h, then h is not a unity, then we will get the black curve. We get this in 20 log g minus 20 log h, right? Just simply the subtraction. That's why I got the black curve just shifted by 20 log k. So my UGB is also changed. My pole will not change, but the UGB will change due to omega u by k definitely. And this is till the omega u, and then after it I have a pole P2 and 0 Z1. So let's see this effect here. So while a closed loop transfer function, in a closed loop transfer function, we already have seen that below the UGB of the loop gain, my gain will be a only depend on the feedback factor, that's the 20 log 1 by k, and the above the UGB my gain will be this G, will follow the G curve. So that's why I plotted in the blue curve this like this. And if I plot the phase Kara of the unity feedback, then at the pole P1 I will get 90 degree. Again at the pole P2 I will get another 90 degree, this one. At the 0 I will get this. So due to the 0, what's happening? Due to the 0, if my 0 is this near to this, what's happening? This fellow will do like this. Do like this. It will reduce my phase margin. So that's why I have told you that by adding a 0, zero, means there is a zero in RS plane, and it adds the phase lag in the system, and due to that, my phase margin degraded. So that's the thing. So one more thing is that similarly, if the P2 is closer, similarly the P2 is closer to the UGBC, P2 is closer to UGB, the phase margin is degraded, and the degraded phase margin we already have seen that it will create a ringing. So we have already seen that the delay, adding a delay in the closed loop path, that means that there is a pole and zero in the closed loop, zeros and the poles in the closed loop path. That means that will add the phase lags in the closed loop path, and that is creating phase lag, and that's result into the phase margin, different value of the phase margin. That's the link I want to create in your mind. The phase margin, ringing in the step response, pole locations. That's the map I think you have clear now in your mind. So we want the first order response. That means that I don't want any of this bloody fellow near to UGB. I want to kick out this bloody fellows P2 and Z1 out of UGB, so that it will not deteriorate here and deteriorate my phase margin. Right? That is the thing I want to make the system always stable. Oh, now let's make op-amp transistor step by step, and then we will analyze the different specifications of the op-amp. I think it will not take more than 40 minutes. I think we will end up into the right time. Maybe let's try. So here, this is an operational transconductance, and that we already have, that we want to build, right? So we need a two different input. Let's say the simple MOS devices, we have V1 applied here, the V2 is applied here. I will get the GM times V1 minus V2 current. That's the requirement I got satisfied. That's why I want the current is equal to GM into VD I want. But the problem here is that the impedance looking from this fellow is 1 by GM. And impedance looking from this fellow is infinity. So that is not match here. I want the impedance infinity. So what I have to do, I have to add one extra buffer here, and that extra buffer I am adding here, and that extra buffer output impedance also should have a 1 by GM. Output impedance from this also 1 by GM, because impedance should match here, and this have impedance here. This must have the impedance here, infinity. So how can I do that? I have that fellow. We already have that fellow, this common drain. So in the common drain, we see that the impedance is infinity. Impedance looking from source is 1 by GM. This matches my requirement. So let's plug it here. V1, V2. Oh, I get the dip pair. Yes. Now, what I have to do? Sir, I have to bias these things also. Because at the biasing point, we are approximating to the linear one, and we need a biasing, right? We need a biasing to proper biasing point. So let's bias through the resistor. But you will see that after later words, the common mode rejection ratio, there is a one term that depends on this resistance value. I need this common mode resistance rejection ratio infinity, and it's directly proportional to this R. If the R is not too large, my CMRR will not too good. I mean, and why the CMRR is good, we will talk about later. Just take a note that from the CMRR perception, I need this fellow to be a very large infinity, ideal. So who will give me this infinity resistance? Current source. We have a current source output impedance infinity. So let's plug the current source here. I have plugged the current source will bias this transistor. The current source carries the current I0. This bloody fellow will have in a VCM, means at the same input, I0 by 2 is bias, right? It will bias by this way. Let's assume this thing, so let's analyze this thing in the differential manner. So if I have a V1, if I have a V2, I can decompose V1 into this term, average term V1 plus V2 by 2 plus V1 minus V2 by 2, and this term V1 plus V2 by 2 minus V1 minus V2 by 2. So this thing V1 plus V2 by 2 is nothing but the average value. This is a common mode voltage, we can say. And V1 minus V2 by 2 is difference voltage, VD by 2. And here is VCM minus VD by 2. So this guy, I can decompose these things. And due to the VCM, when I am applying here VCM, so what will happen? The current is I0, the same value of the current I0 by 2, it will get both the transistor bias. But if we apply the differential signal plus VD by 2 and minus VD by 2, plus VD by 2 and minus VD by 2, so here I will get the current based on this node. But this node actually, in that sense, what will you see here is, let's say my VD going in this direction, this fellow as a common source phenomena going in this direction, my VD by 2 is minus VD by 2 going in this direction. Apply the common source phenomena, source follow phenomena, sorry, source, this will go this, add this fellow is sourcing, this pumping this, pushing this Vx upward, this fellow pushing this Vx downward, so Vx will be at constant value, and that we can consider it as a AC ground. This is a, by intuitive way you can say, otherwise you can say mathematically also, this is both are the symmetric circuit, both are the symmetric circuit. Antisymmetric excitation you are giving here, Vd by 2 and minus Vd by 2, so this node will be at the AC ground. So you apply the Vd by 2 here, then the current will be flow in that direction, which will be Gm Vd by 2. Here, if we apply the minus Vd by 2 here, the current will be flow here minus Gm Vd by 2. That's the thing. So yeah. Now, what is the thing we needed here? We need a single-ended output. But let's see, धीरे धीरे है ना, let's see, connect the resistor here. If we connect the resistor, the gain, that Gm Vd by 2 current goes through here, so we will get the V output 1 is equal to Gm Vd by 2 into R. Here V output 2 we will get same, Gm Vd by 2 into R. So finally V output minus V output 2 minus Gm into R. But we want a single-ended output, or again I am not satisfying this R, because implementing R in a chip, it's a difficult thing. The implementing a MOS is a funny thing as compared to the R, because it takes the less area, less steps also, right? And accurate value of the R is also not going to be happen there. Means there is a very large variation. So means it's happened, but yet too much cost. Not, it's not possible that not happen. It's happened, but yet the too much cost. So now the thing is that I have implemented that thing with the MOS. So what will happen with this? The happen with this is that Gm into Vd by 2 current actually flows through this. If you look into this side, the resistance is ROP. If you look into this side, resistance is RON. The output resistance is ROP parallel RON, and the gain is minus Gm by 2. But I want again the single-ended things. So what I have done here, simple. Whatever the current I had Gm Vd by 2 in through this branch, I have mirrored that current here from the top node. So this node is pumping by this current GMVD by 2, this is mirrored by this, and from this here, oh sorry, and from this we are getting a current GM into VD by 2. So finally we have a current GM into VD, and that's what I want. So this is my OTA. This is my OTA, but it has a finite output impedance. So what is this output impedance value? That also we can derive actually, but please do it with yourself, because it will take a time. So I want to skip it. Its output impedance is by looking this R up and R down. You will get that is ROP parallel RON. So finally, yeah. This is a R output. This is a RO2 parallel RO4. And if we see the equivalent GM by considering the cap, so see at every node we have a capacitance. Here is also a capacitance. Here is also we have a capacitance, is including the load capacitance and parasitic capacitance. Here is also a capacitance, but the capacitance here is not significant, because but the capacitance here is significant. Why? Because it CE includes
Hello.
and CG. So is it plausible? So this is the thing. If you derive this expression of the y, I will not derive here. Means I already derived here, but just want to tell you that due to this pole capacitance, larger capacitance here, if you see the equivalent impedance, here is 1 by GM3. Here is capacitance is GE. What is the R? R is 1 by GM3 and capacitance is C. You will get a pole there. Due to this, you will get a pole as pole P3. That is the pole P3. And due to that, one more thing that I want to show you, here's a two parallel orange path I have shown. You will get a 0 due to that, and the 0 is GM3 divided by C, that you will see here in the transfer function. Please derive it yourself. Right? So this is the thing. Now the offset value. So what is the offset actually? The meaning of the offset is even though both the input are shorted to the ground, I will get some current at the output. And if I want to measure at the input referred offset, that the VOS, that VO is nothing but the IOS by GM. Yeah, so this thing, IOS by GM. So that is the thing that I want to measure. And what is why we are getting an offset? There is two reason of the offset. Actually, systematic offset and the random offset. In the random offset also there is a two thing. Due to the beta mismatch and due to the VT mismatch, you will get an offset. You will get the many papers and many in the Razavi also you will get in the last chapters. So please go through that. Mostly this VT mismatch is getting dominated. So let's consider here, and that VT mismatch we can consider into the overdrive. So VGS minus VT is nothing but the overdrive value, and we can consider this in that way. So here VT mismatch between the 1 and 2 is delta VT 1 2, and VT mismatch between this 3 and 4 I have 1 2 3 and 4 delta V 3 3 4. So the current offset current due to 1 and 2 is GM1 into delta VT 1 2 plus or minus, because it's an random nature, we don't know. And so due to this GM3 delta VT 3 4, and this is the output current I am getting, but I want the input referred offset voltage. This is this divided by GM. If you divide by GM, that is equal to delta VT12 plus or minus GM3 by this. So the point is that if you reduce the offset voltage, we have to increase the GM and reduce the GM3 by increasing the GM1 by increasing the W by L, but it will add the capacitance also, increase the capacitance also, right? Reducing the GM, that means W by L3 you have to reduce. But W by L3 you will reduce for the same amount of the current. The overdrive value will increase and then reduce the swing. That we will see. Now let's consider the swing point of view. The swing point of view, how much the margin we have? VDD minus VOV4. That's the upper limit. What is the bottom limit? Bottom limit is this is a VCM, and the drain is always a one VT down than the gate. So this is VCM minus VT to this. So this is the output range. Output swing range. What is the ICMR? So ICMR is the input common mode range. So input common mode range, in that the minimum input common mode range actually here is the VOV of this transistor plus VGS of this. VGS can be written as always VGS can be written as VOV plus VT. So right, this is the thing, VOV plus VT plus VOV, and from the top side we can see that VDD minus VSG3, the VDD minus VSG3 and plus VT, because the gate is always the higher VT than this. So this is the thing. So this is the ICMR. This is a simple equation you will get. The point is that let's increase the gain of this transistor. OTA means two-stage op-amp. In the two-stage means why we need to go for the second stage. The second stage already contributing some gain also, and we already seeing that I want the GM into VD current that passes to the CC, that kind of the thing. So that's why let's go for the second stage. But in the second stage, what should I connect, PMOS or NMOS here? So here VDD minus this point is VDD minus VSG3 at I0 by 2, and this thing is VDD minus VHS I0. If you connect the NMOS, then it's simply VDD. This is compatible, I think. From the voltage point of view, this is compatible. So let's go for the PMOS current, so common source amplifier with current source as a load here. So now I have built the op-amp, but the thing is that we already have seen that we have reversed the direction there. Plus this side and minus this side was there, but we have reversed this way because we need current in this direction. So that's the reason we have reversed. Even from the gain point of view, you can see that I need a positive gain here. So this is a common source amplifier, and common source amplifier always have a 180 degrees phase shift. So minus 180 that will give. So that minus 180 you can give here. So I will get positive thing. So that's the thing. So from this, you can correlate this thing with this without CC, and if you find the pole and zero, you will see that the pole P1, P2 are not that much separated. So phase margin will get degraded. That's why I have to add the capacitor here. To make this pole larger. The pole here P1. Actually the C1 I am increasing making the P1 lower, that means making the dominant pole. That means that previously it was this P1, P2. Afterwards, what I am making this P1 here and making this P2 here. That means I am splitting a pole. Splitting a pole. Right? There's a pole splitting. Miller compensation is also known as a pole splitting. So that's what I am doing here. So they are adding, and even it adds the zero. So that's why I have added zero to compensate that zero. And if you derive this pole expression here, so you will finally get same way, same way. The equivalent impedance this equivalent capacitor, the equivalent impedance equivalent capacitor. You will get the zero GM1 by GM6 by CC, UGB same first transconductance by CC. Just you have to relate these things. Just you have to relate these things with that our model, block diagram model. So from that you can easily get this poles and zero intuitively. This thing intuitively you will get. That's why I have spent too much 1.5 hour time in that thing, right? Because from that thing this the derivation is very easy and understanding is also very easy. Now, coming to the point of offset, we already seen that there is a systematic offset. So how systematic offset we will get? See, here VDD, this port potentially, oh sorry, this is getting deleted. It is no. Yeah. So this point is there VDD minus VSG3 potential, and this potential is VDD minus VSG11 at a different current. Both are at the different current. You can see here. So you will get the offset here, and that will offset will propagate, and you will get the offset at the output. So we don't want that. So to reduce this offset, this condition has to be met. To eliminate that systematic offset, this condition has to be matched. Right, and the second thing, the input referred offset, random offset. This random offset we already did the input referred offset VOS1, VOS2. If you go through the expression here and input referred, that means derived divided by the total gain, then you will finally find that the offset of the two-stage op-amp is equal to the offset of the first stage plus or minus offset of the second stage divided by gain of the first stage. This is a 2 higher, so that we can approximate the offset equal to single first stage op-amp. That is the thing, and first stage op-amp we already derived, right? Delta VT 1 2 plus or minus GM3 by GM1 delta VT 3 4. This is the offset of the first stage, right? And to reduce it, we have to increase this fellow, we have to decrease this fellow, right? Now coming towards the second point, that is a slew rate. So in a slew rate, you have to connect this op-amp in negative feedback configuration and apply the step here. And here is a gap. And see these things, how it's behave. So actually what happened, so during this positive step, what will happen, the blue curve will follow, current path will follow the blue curve, and this capacitor C, and this due to the virtual ground, this yellow green color I have shown this node as a virtual ground, that you can get it from that block diagram thing, right? So the current will flow through the here, and my slew rate will be I naught by C. Because what is the slew rate? Is nothing but I equal to C du by dt. Du by dt is the slew rate. Is nothing but the I naught by C. Similarly, from the discharge path, you have two discharge path here, the pink line. From this fellow to the M3, M1 and this, and again to this M7. So there is a two-way. So slew rate minimum, you will get the what is the minimum value at I naught by C and this. That is a thing. Now common mode rejection ratio. So let's discuss this. The common mode rejection ratio is a differential gain by common mode gain. Ideally, we don't want the input common mode signal here that is to be amplified and go to the output. We need common mode gain to be as low as possible. That means that this is a very low, that means that this fellow is more. This is we want. So basically the CMRR of the two-stage op-amp is nothing but the CMRR on the first stage op-amp itself, because the common mode signal comes from the different signal, and that is at the first stage, right? If we the differential gain is already we know minus Gm into R. The common mode gain if we derive, so here the common mode gain is derived, that is simple, nothing in this phenomena. The common mode gain is nothing but this. The resistance looking from the drain, this is common source amplifier with source degeneration. Resistance looking from the drain divided by the resistance looking from the source. Resistance looking from the drain divided by resistance looking from the source. All these things I got from the intuition, that is from my practice. You can, I am telling you because you also need to have to develop a practice if you want to be analog designer. So this is a common mode gain. If we derive, see that the common mode rejection ratio is nothing, depends on the ROI. As I already told you, it depends on the RO. If RO is more, the CMRR is larger. So RO is more, how we will get VO to use the current source. Simple thing, right? The next thing is the PSRR. Sorry. The next thing, PSRR. The PSRR is nothing but the differential gain considering the VDD is 0 divided by power supply gain considering the VN is 0. That means that simple unity feedback configuration if I am applying, and if I am applying a perturbation in the VDD. If I am applying a perturbation in the VDD here, so what I will get the perturbation in the V output. This thing I have simplified here. So V output divided by VDD, I will get this expression is equal to 1 by PSR plus. In the industry, we usually plot simply by this way. Just giving a perturbation here, connect into the negative feedback and see the perturbation here, you will get the V output by VDD. And that is a 1 divided by actually PSRR plus, but we will get the curve like this, like mountain, and this is at GB. Oh, where this fellow gone? This is a GB unity B, and this is at pole P2. So come here, you will see that thing how. So you can see, observe that, and the PSRR curve is ulta of that one. Ulta of that one means this is a thing. So this is at GB, this is a PSRR curve, and that's the T2. I think I have drawn here somewhere. No? Yeah, I have drawn here, yeah. So what happens, just intuitively we have to see that there is a derivation for this in Alan Holberg book. But I want to tell you intuitive way what is happening. See, this fellow, I7, this current is coming from this current mirror, right? We have this fellow is coming from this current mirror. The I7 is fixed, so the same I7 has to flow to the I6, right? And to support this current, we need the same value, some constant value of the VSG here. Now to make a constant value of VSG, and I am applying a perturbation here in this fellow. So what will happen? This node also has to follow this perturbation. At the higher frequency, this fellow is sorted. This perturbation directly coming to the output. That means that at the higher frequency, my VDD perturbation directly go at the output. That means the gain is approximately a very less gain. We can say 1. That's why you can see here in this graph. At the higher frequency, this fellow PSRR fellow is decreased, and that is what the disadvantage or cons of the two-stage op-amp. To eliminate that cons, we have to go for the folded cascade op-amp. In that thing, for the larger range of the frequency you will get. So that is the thing, right? Now let's in some minutes we have some time, and the final step is there. Now design the two-stage op-amp. We got all the things clear in our mind. So the people will give us a specification: input common mode range, slew rate, UGB, gain, common CL, output swing, phase margin, power distribution, and from that thing, what we have to decide the sizes of the transistor 1 to 7. The size is, that means W by L. That we have to decide, and that's called the designing. And see, for the designing, we are actually, let's do the step by step. It will hardly take the 15 minutes, not more than that. So based on the ICMR, so if the ICMR is given like this, if it's a minimum voltage to VDD, let's say 0.8 to 1.8, then we have to go to the end, we have to select the topology. Then we will select the input ND pair. Why? Because for the ND pair, we know that the minimum value is required here, VOV plus something VGS. That is satisfied here. That's why we have to go to the MB pair, because if this kind of the thing is there, VDD, V minimum is 0. Can I go for the ND pair? No. So for if my V minimum is 0, I should go for the, see, V minimum is 0, V maximum is some voltage. So we have to go for the PD pair, because this input can go, PMOS input can go as low as 0. So that's why I have to choose the PMOS topology. So this is also, see, this all these things cover many interview questions till now. If you go, if the interviewer asks for the two-stage op-amp, you have mentioned in your resume that I have designed a two-stage op-amp. They will, or they or he will ask you all these questions to you. So this is very important for the interview also, as I already told to you. Now the phase margin. So phase margin, I have plotted here the loop gain, P1 omega u, and again P2 minus 14 dB per decade, and C1. And see here, when I have told that it's P2 near to the UGB, I will P2 near to the UGB, my phase margin 2. This red curve and the black curve. For the black curve, the P2 is far away from the UGB. For the red curve, the P2 is near to the UGB. So you can see that the phase margin is less. The phase margin PM2 is less than PM1. So let's derive. What is the phase margin? 180 degree plus angle H, angle of GH as omega GC. This three term is it's adding a phase to u in the transfer function, minus tan inverse of omega u by P1, minus tan inverse of omega u by P2, and this thing. But this thing omega u by P1, the phase due to the pole P1 is already 90 degree here. So you can take here already minus 90 degree. So this finally you will end up into this expression. But you will see in this also omega u by z. The omega u is already gm1 by c. Z is also gm6 by cc. So this is also omega u by z is nothing but the ratio of the transconductance between the gm1 and gm6. It means the ratio of the transconductance between the first stage and the second stage. But we need this zero practically to be a very large than the omega u. That means we don't want to affect our phase margin. So gm6 is larger than gm1. So let's assume that I assume here the gm6 is 10 times the gm1. So this term will be a tan inverse of 0.1, 5.7 degree. So phase margin equation will get reduced, and now it depends on this phenomena. So point is there, based on the phase margin specification, you will get the relationship between omega u and P2, and that relationship will help you to get the relationship between the CC and CL. Because see, omega u is what? GM1 by omega u you already know. GM1 divided by CC. Pole P2 is a larger expression, but approximately is GM2 by CL. So if we'll put there is GM6, and if you already assume that GM6 is 10 times GM1, so you will get the relationship between CC and CL is this. So phase margin 60 degree for condition that 0 is the 10 times of UGB, you will get this CC. CC must be greater than 0.22 CL. You know the CCL, you will get to know about CC. Similarly, for the phase margin 45, this is the relation and you will get this. So from the phase margin and the CL, we can get the value of the CC. That's what I want to tell you. From the slew rate and the CC, because the slew rate is I naught by CC. From the slew rate and the CC, I already got, you will get the know about the I naught. And then from the ICMR plus, what is the ICMR plus is VDD minus, we already derived this expression. The unknown thing is this thing. This thing is unknown. K is what? Mu P cos of W by, we don't know this ratio. Baki, all these things, ICMR, VDD, VT, we all know these things. So from this we can get the W by L3 and 4. And UGB is GM1 by CC. We know UGB, we know the CC, we got the GM1. But again the GM1, we know the value of the current, I naught, and this I naught by 2. And so we can find the value of the K here. And from the value of the K, we will get the value of the W by L1 and 2. And ICMR minus is what is the VGS1 plus VOV. So here this thing is known to you. This thing is known to you. This thing is unknown. So from the unknown, actually no. Actually this thing is unknown. VOV. You know these things, right? WL1 and I naught you already know. So you will get the VOV here, and from the VOV you will get the WL. So here the first OTA get completed. Design of the first OTA. See, this all these things what we are completed I am telling, but this is with approximation, because the real model is a different thing than the square law model. So this is just the approximate value we are getting. After it getting this value and putting into the simulation and running, you will get mashup also. So you have to tune that thing also. So intuitively you have to know about the thing, which transistor affecting which parameter by that way. The another thing that we have is pole P2 UGB relation from the phase margin point of view. Phase margin point of view, this relation you have, right? And again this relation you have from first stage and the second stage. VSG3 is equal to VSG4. So from that relation, you will get to know about from the equation you will get GM6, and from the GM6 you will get W by L6. From that you will get the I6. Once you know the I6, you know the I7, and from that equation, because the I6 and I7 is a current mirroring action, you will get to know about the I7 value, W by L of I7. But that again, if there's a different way, actually that output stage actually has a V output maximum and V output minimum. So V output maximum, that means that I have a VOV value. From that VOV value also you can get means from this upper limit also, you will get the VOV value, and from this VOV value you will get also W by L6 value, and then you will get the current I6, and that current you can use from to find the W by L of this transistor. This is also one way, but you have to see that actually this current here is flowing through the VDD. What is the power dissipation? And that current through the I5, that bottom transistor tail node, is also contributing into the power dissipation. So this is the power dissipation, you have to take care of it. Your current should not be at that much larger. Now, this is again what I have simplified it simple. I have just actually RO 1 by lambda into I. That term I have mentioned the game here. More than and lambda is proportional to 1 by L. So this two transistor is actually deciding the UG. This two transistor ICMR plus. From the ICMR plus and pole P3 we are getting the sizing of this. This transistor deciding a slew rate. This is V output minimum. This fellow deciding the phase margin. And this fellow deciding what? V output maximum, phase from the phase margin we got this relation also, P2 and omega U, right? Then summary, finally, what we need if we want to increase the gain, I can increase transconductance of both the stage, but to increase the transconductance has this relationship, right? GM is equal to under root 2k ID. To increase this, I have to increase W by L, but it's in a root manner. Again, I can decrease the current also to increase the gain, I5 and I6 tail current. Again, to increase the gain is proportional to the RO is proportional to 1 by lambda, and RO is again lambda is proportional to 1. If I increase the L, O is increased, the gain is increased. That's the thing. Regarding the UGB, if I have to increase, then I have to increase this. Why it's cutting? I'm selecting the eraser actually, sorry. To increase the UGB, I have to increase the GM1 and reduce the CL. That's the thing. If you want to increase the slew rate, then you have to focus on I0 and CC. So that is the thing, and this is a simple GM3 equation you have to remember, because that will help you in designing. So that is the thing from my side. If you have any question, you can ask. Sorry, let me drink water. Hello. Hello. Hello.
Yes, sir, you're audible.
Yeah.
Yes. Is there anyone who has any query?
Actually, this is a 40-hour course, that's designing of the two-stage op-amp, that I have told you in just a 2 hours. So definitely for the most of the people, you will not digest these things. But at least I was trying to get the intuitive feeling of it. It will help you definitely if you study that course. Yeah.
Sir, is there any way to reach out to you afterwards in case we have any doubts?
Yeah, sure. You can reach me on email, even on FB, even on LinkedIn. Even I will share my mobile number and email ID to you.
Sure, sir. Yes, sir. In case you have any doubts, then we'll reach out to you.
Sure. You can. Yeah.